Hello, in this video we're going to look at our last reaction of carboxylic acids, and that is the conversion of a carboxylic acid to an acid chloride. And this reaction is actually pretty important in our next chapter on carboxylic acid derivatives because it's hard to turn carboxylic acids into carboxylic acid derivatives, but it's quite easy to turn the acid chlorides into various carboxylic acid derivatives. So essentially we're kind of going uphill in energy via this reaction. Okay, and so I'm going to go over a general form of this reaction, give you an example, and then I'll go over a mechanism because it's a really good demonstration of nucleophilic acyl substitution mechanisms. Okay, so our general reaction here is we're going to have a carboxylic acid with some alkyl group here, and we're going to react that with thionyl chloride. All right. You could also do this with oxalochloride, but I'm going to show the mechanism for thionyl chloride and focus on that. All right. And what that does is we replace the hydroxy group with a chloride. Okay. Thionyl chloride looks like this. And you'll see it again soon in the mechanism. Okay. That's what it looks like. There's a couple more pairs on the oxygen. But what we have here is a sulfur that's very electrophilic. Okay, and has some good leaving groups attached to it, and that'll be really important when we get to talking about the mechanism of the reaction. Let me give you a couple examples before we get into the mechanism. And just like when we were using thionyl chloride with alcohols, we're replacing the OH with the chlorine. So I can think of your favorite carboxylic acid here, right? 2, 3, 4, 5. Maybe it's pentanoic acid. And I can take thionyl chloride, and I'm just going to substitute that hydroxy group with the chlorine. Maybe I want to be more interesting here. I'll use a benzene ring. Okay. Make this carboxylic acid. Thionyl chloride, and voila. Make this. Now, one thing I forgot to mention when I did the general reaction, the reason why this works so well is the byproducts. So we're making sulfur dioxide, which is a gas, and we're making HCl gas. And so both of these are going to, because they're gases, they can bubble out of the reaction. And essentially, we're making use of Le Chatelier's principle. We are removing reactants, and so that's going to, we're removing products, so that's going to drive the reaction to the product side. It's going to shift the equilibrium to the right. Okay. We'll have the same thing here. And also, because these byproducts are just bubbling out of the reaction, that makes the separation easy because it's happening for us while the reaction is occurring. All right. Organic chemists love to do anything they can to make their purifications easy. Okay, so let's look at a mechanism of this reaction. Okay, and essentially what we are doing here is we're doing two back-to-back nucleophilic acyl substitutions. The first one is going to make oxygen a good leaving group, and then the second substitution, we're going to substitute out that leaving group. So I'm going to start with I'm going to use the simplest carboxylic acid possible here in this mechanism. Okay. And this is acetic acid. Okay, this is what's in vinegar. All right, just to make my life easier here. And the first thing that's going to happen, if you remember earlier, I said this sulfur is very electrophilic, the sulfur atom, because of the presence of these electronegative atoms and kind of analogous to a carbonyl. We could draw a resonance form that would put a plus charge there. Okay, and so our lone pair nucleophile is going to attack that, and we're going to do a nucleophilic addition. And initially, that gets us to here. You have to be careful here. It's really easy to lose track of the lone pair on that sulfur. I do it sometimes. Okay, so we can do that nucleophilic addition, and then we have a good leaving group on the sulfur, so that can leave. And that's going to be a nucleophile elimination. All right, and that gets us to here. Ooh. This is a mechanism you have to be patient with because there are many steps. Okay, so we make that. All right, there's a plus charge on this oxygen. Don't forget that. All right, and this has a resonance form. Okay, so we can delocalize this lone pair on this oxygen. I don't know if you can see it, but it's there. Okay, and if we do that, we move this pair of electrons onto this oxygen, then we run out of room on the board. Okay. Charge here. All right, and I'm going to have to erase this stuff up here to get to where I want to get to. All right, so nucleophilic addition, nucleophile elimination, and then we're going to take, we eliminated a chloride ion. And we can do a proton transfer. Right, so this is making our HCl at the same time. Proton transfer. And then what that gives us is kind of a halfway point on the mechanism, someplace where you can kind of hang your hat. You can remember how to get this one place you're going to get to. So we get to here. So we have substituted one of the chlorines on the sulfur, the thionyl chloride, with this carboxylate. So that was our first nucleophilic acyl substitution. There was a nucleophilic addition followed by a nucleophile elimination followed by a proton transfer. And that gets us to what's called a chlorosulfite anhydride. Anhydride means something that's missing a molecule of water. Okay, we'll talk about anhydrides more when we get into chapter 21. Okay, and then we can now do kind of the second half of the mechanism, which is another nucleophilic acyl substitution. Okay, so I'm going to erase this here, and we're going to start the next part of this mechanism with our chlorosulfide anhydride. The point of this was now we have an oxygen that's a better leaving group than the hydroxide. Okay, so now we're going to have chloride ion come in. We're going to do this step, which you might recognize as a nucleophilic addition. All right, and that gets us to a tetrahedral intermediate. Oh, and I'm gonna run out of space here. I can tell already. Okay. This is a long molecule. There we go. Tetrahedral intermediate. And then we can do our last step in the entire mechanism. Okay, the lone pair on this oxygen swings down, and we're going to eliminate all this. This is going to go here to form SO2. Okay, and the chloride is going to leave. All right, and so I'll take us over here, and that'll get us our acid chloride plus SO2, sulfur dioxide, which just that molecule itself, this would make an interesting Lewis structure and molecular geometry problem, but that's not the focus of this part of the course. And then the chloride ion. Okay, and then this in another part of the mechanism picks up a hydrogen. All right. So that concludes our